Hi everyone, we are back and we are on to Lecture 5, Linear Algebra and Solving Systems of Equations with Applications to Solid Mechanics. So, we are going to get into a little bit of linear algebra and really applying it to how do we solve systems of equations, how do we set up and solve systems of equations, how do we diagonalize matrices and tensors, how do we work with eigenvalues, eigenvectors, and all types of fun rotations. So, the first thing that we want to kind of encounter is what is basically, what is a scalar? Scalar, what is a vector, what is a matrix, and what is a tensor. A scalar quantity is just a value that has a magnitude with no direction. A vector will have both magnitude and direction. So some examples of vectors are force. So force, and then you usually have that like little hat over the top. Force can have like basically 1, 2, 3. In 3 dimensions, it will have a direction associated with it, with a 1, 2, 3 axes or whatever, X, Y, Z, etc., etc. So it'll have both a magnitude and a direction. We could take that with just basically looking at the norm of F. But anyway, a matrix, on the other hand, you've probably seen before. This is a matrix, effectively. Now a matrix does not have direction associated with it. A tensor, on the other hand, does. So in tensor notation, for example, this sigma ij, where ij are essentially indices that indicate direction. So you can have a second-rank tensor. There's lots of second-rank tensors, solid mechanics. So stress, strain, diffusion. There's actually quite a few second-rank tensor properties. You can have a fourth-rank tensor property. We'll see that a little bit later on. Or third rank, etc., etc., etc. So second-rank tensor property in 3 dimensions would be a 3x3 tensor, effectively. So these are kind of the differences. These are very important as we get into kind of linear algebra concepts. So let's go ahead and let's start to look at just a matrix. So again, we could look at matrices in matrix form. We could look at another matrix, again, variables as well. You see here, F is a little interesting. I'm going to clear F. That's bothering me. So get those values. And I can have a 2x3 matrix. So again, remember, 2 columns, 3 rows. So it's confusing because again, we call out, if we're going to extract values, it's basically rows and then matrices. But anyways, so we could have M4 as well with values. I could also have, basically this is, similar, a vector. It's like force. So I can dot matrices. It's one of the important things to look at. Again, dimensions is going to be critical here. Dimensions of M1, dimensions of M2. 3x3, 3x3. If my matrices have similar dimensions or compatible dimensions, I can start to do operations on them. So I could do M1, and I could visualize this in matrix form, as you can see here. M1, M2. I could do M1. I could always do scalar operations on anything. I could do +1. I could do exponential of M1. I can do lots of, again, I could do lots and lots of different, mathematical operations. I could do square root. So you can do all types of mathematical operations here. But the important one is going to be dotting. And we're going to see that in a second. Because essentially that is going to multiply it versus what you're looking for in terms of the variables that you're looking for as well. So I could dot 2 matrices together. These will be very important essentially also when we get into rotations. So I could dot 2 by 2. I could dot 2 3x3 matrices, and that's going to give me a 3x3. So you're going to see kind of what are the dimensionalities that we can get. I can also transpose a matrix. So if I look at M1 matrix form, the transpose is basically just flipping everything across my diagonal. So here on my diagonal 1, 5, 9, those values remain the same, but I just flip those other ones. So those are going to have interesting properties. The transpose is going to be identical if my matrix is basically symmetric, which we'll see is the case often. Matrix is symmetric, then transpose of M equals M. And that's a very unique property. I can calculate the determinant. And for this matrix, it's 0. That's a problem. I could do the trace. What is the trace? Trace is adding basically my values here. So it's going to add this, this, and this. So my diagonals. So I could do the trace. So determinant, and again, trace, I could do the inverse of my matrix. Oops. Why doesn't it give me the inverse here? Well, it doesn't give me the inverse here because I cannot calculate the inverse if inverse if determinant equals 0. So that's kind of a property again of matrices and all those values. I could do the conjugate transpose. Again, there's lots of other operations. Again, let's look to, if I do m1.m3, so let's look at dimensions of m1. So if I dot if I dot a 3 by 3, m1, m2, actually m3, excuse me. If I dot a 3 by 3 by a 2 by 3, it's going to lead to a 2 by 3. So I can still dot and perform those operations. So let's look at M3 again. X1, M1. So I can still dot those. Those are compatible shapes effectively, and that will give me a 2 by 3. However, I look at, what are my dimensions of M3, dimensions of M4. I can not dot these values. So dot incompatible dimensions, they will not work. So I cannot dot those values. So I can do m1 times x1. Remember, x1 was just our what? It was a 1 by 3. So if I do, for example, a 3 by 3 dotted with 1 by 3 gives me 1 by 3. I cannot do, again, m3.x1, again, incompatible shapes, the 2 by 3, as we kind of saw here. And you can do the same thing with m4. And again, can't get those because it's a non-zero value. All right, so that's just kind of some, basically just some introduction to matrices, some of the operations, dotting, making sure that your values are compatible. And now we'll get on to the next time of solving equations using some linear algebra concepts. All right, see you next video. Thanks. Bye.